My name is Javier Varela. I'm here representing a research team. The members of the team are the Dr. Juan Pablo Nogues, the Dr. Christian Scher, and me. First of all, I would like to thank the organizer for the invitation. Today I'm going to talk about the influence of the intrinsic permeability model in a buoyancy-driven CO2 plume, but including a very interesting phenomena which is called capillary heterogeneity. The outline of the presentation: first, the aim of the work, the motivation. Then I will define what is capillary heterogeneity, how much affects the inclusion of the capillary heterogeneity, how can we generate the capillary pressure field. I'm going to present the set of equations, the mathematical model, some results, conclusions, and future works. Well, the aim of the work is basically to determine how much the permeability model influences the buoyancy-driven CO2 plume, considering, of course, the capillary heterogeneity. Well, the main field of application is the CO2 injection, the carbon capture and sequestration process. In figure A, we can see the typical injection process. And in figure B, we can see the four types of trapping mechanisms. The structural trapping, the residual trapping, the solubility trapping, and the mineral trapping. Our model only takes into account the first two, the structural trapping and the residual trapping. We are not including the solubility process. Okay, so what's capillary heterogeneity? First, I would like to show this schematic representation of 4 cell grids, 1, 2, 3, and 4, with the same entry pressure, okay? So the 4 cells have the same entry pressure. In the figure B, we can see a typical capillary pressure curve. The capillary pressure versus the saturation of the wetting phase. And we can see one single curve that stands for the 4 cell grids. This was generated via the Brooks-Corey correlation for the same physical parameters, lambda and entry pressure. But what happens when we have different entry pressures? So in figure A, we can see, again, 4 cell grids, but in this time with different entry pressure. So the cell grid 2 has the greater entry pressure. The cells 4 and 3 have approximately the same entry pressure, and the cell 1 has the lower entry pressure. So again, we plot the capillary pressure curves, but in this time we have 3 different curves, okay, with different minimum value equal to the entry pressure and the maximum value of the capillary pressure evaluated at the irreducible saturation of the wetting phase. So what's the consequence of considering this capillary heterogeneity? So basically, the CO2 plume surround the areas of high entry pressure. Here in the figure A, we show the entry pressure field. All the region colored in blue has low entry pressure, about 5,000 pascals, and the red zone has higher entry pressure of about 30,000 pascal. So in here, we show a system initially full with water at the top and CO2 at the bottom will go upwards buoyantly. Okay, so basically the CO2 will surround this area due to the higher entry pressure of this zone, of course. So how much affects the inclusion of this phenomena? These are the results of Sadat from the University of Texas at Austin in 2009 that include this phenomena and compare with a homogeneous capillary pressure field. In figure A, we can see a simulation for 25 years without the inclusion of the capillary heterogeneity, and B, with the inclusion of capillary heterogeneity. As we can see visually, the pattern of the flow is quite different. Okay, is more ramified than the figure B is quite more ramified than the figure A. And the main consequence of the inclusion of this phenomena is that offers a large barrier to the flow of the CO2. That's why Sadat proposed in 2010 this inclusion of the capillary heterogeneity as a new trapping mechanism called local capillary trapping. Yeah.
In B, do you have some kind of a probabilistic distribution
of the permeability field? Yeah, they apply a multivariate Gaussian field in order to generate. I think this has a stratification ratio of longitudinal to transfer of 3. Yeah, this is.
so then you distribute that over the whole field.
Yeah, yeah. I'm gonna explain how to generate the heterogeneous entry pressure field from the intrinsic permeability field. So basically, this is the process that we need to follow in order to generate the heterogeneous entry pressure field. First, we have to set some average or mean values of permeability and entry pressure. Then we have to generate an heterogeneous intrinsic permeability field via some correlation. Then we need to generate an heterogeneous porosity field, and the porosity field should be somehow dependent on the permeability. Then we apply the leverage J function. I'm going to explain what is the leverage J function in order to sort of extrapolate the data that we have initially to each cell in order to generate the heterogeneous entry pressure field. So the first step, set mean values of permeability, entry pressure. In here, we use typical values. Mean value of permeability, the logarithm of K equals to minus 15.5. And the mean value of the entry pressure set as 8,000 pascals. The second step is to generate the permeability field. So here I'm using correlation proposed by Sin and Harvey in 2003. They proposed 3 ways to generate an heterogeneous permeability field with log normal invariant conductivity distributions. And these 3 ways only are different in one sense. They're different in how the patterns of permeability or conductivity are connected each other. Okay, so basically we have three kinds of permeability fields. The first field has connected high conductivity structures. The second field is a multivariate log Gaussian field and has connected structures of intermediate values. And the third field has connected low conductivity structures. Okay, so I'm going to use these three fields in order to compare them, including the capillary heterogeneity phenomena. So here we generate the permeability field in order to somehow improve or enhance the vertical flow. We use a vertical stratification, although we know that most of the aquifers has a longitudinal or horizontal stratification. In the first figure, we show this permeability field with low conductivity structures. In the third figure, with high conductivity structures. And as we can see, the stratification is the same, only differs on by which the patterns or paths of high conductivity are connected. For example, here we can see a low conductivity zone, and this is the same, but it has a high value of permeability. And in the middle, we show the intermediate conductivity structures, which is somehow an averaging of these two. Okay? This was generated with a mean permeability that we said before, and a variance of 0.17, and a stratification ratio transfer to longitudinal of 5. Okay, the third step is to generate the porosity field. The simplest way is to use a power law. So we implemented an empirical fit proposed by Holtz in 2002. So here we show the porosity field generated via this power law for the intermediate connected conductivity field. The fourth step is to apply the Lagrange function. So what's the Lagrange function? The Lagrange function was a sort of attempt to extrapolate capillary pressure data for a given rock to rocks that are somehow similar, but with different physical parameters as permeability, porosity, and wetting properties. Surface tension, contact angle, and so on. So this is a very old function. This is in Leverett proposed that in 1941. This is the equation. Basically, the J function is a function of the saturation of the wetting phase. It depends on the capillary pressure that depends on the saturation. The surface tension, the contact angle, the permeability, and the porosity. Okay? So if we assume that this expression is valid, so we can extrapolate the data provided for the mean values in step 1 to the values that we know of permeability and porosity that we generate before. So considering valid this extrapolation, and moreover assuming that the surface tension nor the contact angle varies spatially, so we end up with this equation. So the entry pressure of each cell, it's equal to the mean entry pressure that we said before, like 8,000 Pascal, and is a function again of the mean permeability, the mean porosity, and the porosity and the permeability and the porosity of each cell. So that's how we generate an heterogeneous entry pressure field. Here we have the heterogeneous entry pressure field for the low conductivity structures, the intermediate conductivity structures, and the high conductivity structures. And it's worth to mention that if we have low conductivity structures, we will have higher entry pressures. Okay, so as we can see in figure A, we have the bigger values of entry pressure, and in figure C, which correspond to the high conductivity structures, we have the lower values of entry pressure. The mathematical model is very simple. We implemented a two-phase flow, incompressible flow in porous media. We have the mass conservation. We're not considering any source term. Then we have, for the wetting phase and non-wetting phase, of course, the multi-phase Darcy velocity for the CO2 and water, the capillary pressure expression, and the sum of saturation equal to 1. So this 6 equation somehow describes the physical phenomena that we're simulating. In order to couple the equations, we implemented an impulse algorithm, implicit pressure, explicit saturation. So basically, we'd end up with a pressure equation. We solve the pressure equation implicitly. And once we know the pressure of the non-wetting phase, we can calculate the total Darcy velocity. And once we know the total Darcy velocity, we can calculate the saturation of the wetting phase for the next step. And then we update the physical parameters of the pressure equation that depends on the saturation of the wetting phase. We apply a finite volume method in order to discretize an approximation of the gradients via TPFA, 2 points flux approximation. Well, this is just an example of how to apply the finite volume method. This is basically the pressure equation, the divergence of the total Darcy velocity equal to 0. We integrate over the volume of the cell grid. We apply the divergence theorem, and we sum the fluxes that enters and leaves the cell. Okay. And this is the impulse algorithm, the discrete version. The results are quite interesting because we expected that the low conductivity structures with high entry pressure field will somehow act as a barrier of the CO2, but we end up with a different result. Here we show the system. The boundary conditions are set to no flow in all of the edges of the domain. This is the simulation data, all the physical parameters. And this is the first result for a low conductivity structure. This is considering the capillary heterogeneity, and this is not considering the capillary heterogeneity. As we can see again, this profile of CO2 is quite more ramified, and it seems that somehow the CO2 finds the low or the easiest path to flow through. So this could be a problem, because if we have sort of fracture here, if we're not including the capillary heterogeneity, we're underestimated the flow of the CO2. Sorry? The average? Yeah. If I average the saturation, or oh,
Laterally, yeah, average laterally.
if I do like a sort of cut here, and no, it's not the same. It's not the same. I'll show the quantification of the volume leaked through a cut in the middle of the domain, and we can see that it's quite different. So this is for the low conductivity structures. This is for the intermediate conductivity structures. In here, we supposed to have a flow that is more somehow enhanced for the greater permeability values, but lower entry pressure. But as we can see, the low conductivity structures allows the CO2 flow to pass through a certain cut more easily than the intermediate conductivity structures. And the high conductivity structures is almost the same as the intermediate. We don't see a huge difference between considering the capillary heterogeneity and not considering the capillary heterogeneity. So this is the quantification of the results. We're measuring the liquid CO2 volume that passed through an horizontal cut of the domain in 5 meters here. And we're plotting this against the different permeability models. In all the models, the consideration or the inclusion of the homogeneous entry pressure leads to a lower amount of CO2 liquid. And the consideration of the heterogeneous entry pressure field leads to a higher liquid volume of CO2. But the interesting thing is that the higher amount of liquid CO2 volume correspond to the low conductivity structures rather than the high conductivity structures, even though this has a lower permeability and a higher entry pressure. So as conclusion, hence the low connected permeability field offers considerable resistance to the flow, to the CO2 flow, due to the permeability and also the entry pressure. The flows, the CO2 flow through, we think that flows through preferential path. That's why we got this kind of results, that the low permeability structures leads to a higher liquid CO2 volume. Thus, for the same simulation time, more volume could potentially reach a fracture. So future works is to somehow perform a rigorous or serious sensitivity analysis to try to quantify the impact of the permeability model as mean permeability, variance, longitudinal stratification, and transverse stratification, to include, of course, the dissolution of CO2, how this affects to the process, include effects of hysteresis, and try to explore some upscaling techniques considering this local capillary trapping process. So that's it. If you have any question.